Welcome, everyone. Thanks for joining us. I know you guys probably just had lunch, so shake it off. We would love this to be interactive, so if you have any questions, please stand up. We can't really see you, so you're going to have to wave at us because the lights are blinding us. And we decided to go, especially for Matt and I, not to go on the stools because we're a little vertically challenged, and we'd get distracted by our swinging feet. So again, welcome to Flow, Fluid, and Flux. You can guess we're probably going to talk about liquid cooling. My name is Christy Olson. I'm the VP of Sales for Data Centers for GCG, and we're an international distribution company. We've been around for over 40 years. We're a little new to the data center sector, but super excited to be here with my esteemed colleagues. I'm going to let everybody introduce themselves. And we're going to do a little fireside chat without the fire.
And the lights are providing good enough. I'm Matt Archibald from nVent. I'm Director of Architecture and Delivery for our liquid cooling product line. Basically responsible for looking at the data center trends in the market, what's going on in the industry, and ensuring that from a company perspective, we have the products that meet the market need now and developing those products in the future. I come from previously with Lenovo and IBM, where I ran environmental planning. I was in charge of power and liquid planning for the better part of 15 years with them, and originally started out as a power subsystem engineer for the Intel server line. So a lot of experience, been doing liquid in the data center since about 2007, direct to chip since about 2012. So a lot of experience with that.
Fun fact about Matt, he lives in Australia and commutes back and forth from the U.S. So he'll be dead in a few years.
Yeah. Ain't nothing living in here.
Thank you, Chrissy and Matt. I'm Ashu Swami, CTO of Marathon, Mara now. Mara is a digital asset mining company, a publicly listed company in the U.S. We operate about 1,500 megawatts of data centers in the US and 4 international locations. We own the entire technology stack, right from the building the chips to the cooling technologies in which these systems are deployed, right all the way up to the orchestration layer and the pool and the cloud where these systems monetize and do the orchestration. So a big part of our technology group is the liquid cooling technology segment, which has very innovative two-phase immersion cooling technologies, cold plate technologies. We're also a consumer of our own liquid cooling products. We currently have 250-ish megawatts of liquid cooling, single-phase immersion liquid cooling deployments in our data centers, and we are ramping them up to more innovative new cooling technologies.
Thank you, guys. So first of all, we just want to get an idea of our audience. How many liquid cooling manufacturers do we have in the audience? You got to raise it because we're blind. Yeah, a couple hands, yeah. How many general contractors? How about engineering and consulting? Operators, end users? People raise their hand like this. Yeah. We can't see you when you do that.
Between contractors and operators, that's the majority of.
Yeah. Awesome. Just like to know who we're talking to. Okay, so we're going to get into the nitty-gritty of liquid cooling, things to think about, questions that we don't usually talk about, right? Some of the challenges that may come about. So let's start out today with, you told me you hear a lot about how do I prepare, what do I do? So liquid cooling today. So in all the forums, you hear everybody's going it, nobody's going to it, people are afraid to go to it, but it's growing, right? And what's driving organizational decisions to explore or deploy liquid cooling?
Workload is the driver. The enabler or the bolt-on to that is the technology and the chips. For the first time in history, now we have liquid-only mainstream silicon SKUs that require liquid cooling, and that just happens to be at the right time, right place, that's a really popular application of technology. So I'd sort of back end that is AI ML is the driver for that, AI in all of its forms. But there were predecessors to that, and that's where I'll hand it off, given your background with Mara.
Absolutely. For Mara, it's two things, TDP and edge. So as Matt mentioned, AI HPC chips, their TDP requirements, Flux is increasingly going up. Over the last 30 years, during the advent of Moore's law, we were seeing the TDP go down, and now for the last 10 years, we're seeing it go up again. In fact, if you look at the NVIDIA GPUs, they're like, the number of transistors in the same centimeter square has increased by only 15%, but the power dissipation has gone up by 20 times, to 2,000%. So that obviously challenges the air cooling technologies and is pushing the envelope on the cooling capacity, and that's why liquid cooling is needed. And the other part is edge. When we are deploying in our mining operations, and I'm sure that happens in AI HPC too, we're deploying these small modular data centers on the edge, on oil fields, on landfills where standard power is available. You need highly scalable, robust solutions to be able to manage these tens of thousands of locations and modular data centers relatively easily. And that requires these edge nodes have very harsh conditions. Sometimes they're in a marine environment or very cold, very hot weather, dust, debris, all those things. And they need very, very tiny footprint. So they can be dropped off in the middle of nowhere without a concrete pad or anything. And only liquid cooling allows that kind of modularity and compact form factor.
So that segues very well into my next question about the perception of liquid cooling. How's that changed? Obviously, remote locations, edge pushes that a lot, but how has it really changed then the perception of it in the last 2 to 3 years?
Before it was a niche. You had HPC scientific workloads, which in the Intel-based with accelerator-type compute, in the accelerator-type compute, HPC Scientific drove that. They had various reasons for doing it, but it was a completely different application. They would know that that supercomputer was coming. They would literally design the room, design the infrastructure to be ready for that installation, and it was a very, very specific. Every single one of those supercomputers that I put in was different. Every aspect of it was different. And now it's commoditized. Like, just to pull an example, an NVIDIA 8-rack, DGX SuperPod GB200, it's 8 racks of liquid cooling. We know what the thermal footprint is. We know what the layout is. It's all common. So that's going to change, and we're going to get away from that as more and more applications go that route. But the benefit of it, sort of being common, is it laid the groundwork for the realization of the other pieces. Now we can exploit these remote environments. We can exploit where air just didn't hold muster, harsher conditions, not needing full pads built and things like that, which can speed deployment. You also get the benefit of reliability. It's been tons of research has gone into it, reliability studies. Liquid-cooled IT equipment has a higher component reliability rate and a higher sustained performance rate, and that's the other piece of this. We are now in a performance chase. The software is caught up with the performance of the hardware, so now this is the other driver as to why do we need these chips? Why do we need all this performance? There's an application case and there's a performance chase, and we're going to continue driving down that path.
Yeah, I think, Chrissy, you should have another question on the performance. That's a big part of liquid cooling, obviously. And Matt, you're absolutely right. One thing that I would like to point out, I never saw this coming last 2 years, how this liquid cooling space and vendors are evolving. One thing unique about this industry is that it's still very much haphazard. It's very fragmented. And if I zoom out and broadly look at it, hyperscalers are running one direction. They have their own custom server requirements, and they will work with the large vendors in APAC or wherever and build commoditized cold plate solutions. No one can sell to them, right? On the other side, you have the new AI HPC demand segment, which is what we are all trying to pursue. We have our own crypto mining cooling problem also to solve, but AI HPC is 10 times bigger than that. And that's where basically all these technologies are competing. And I think it's not going to be a one-size-fits-all or winner-takes-it-all kind of an outcome. It's going to be it's going to be customer segment driven. Telcos will need one kind of a solution. Enterprise servers will need a different kind of a solution. Someone who is operating data centers in Abu Dhabi like we are, where it's high humidity and no water, they will be very focused on WUE in addition to PUE. So there are lots of factors are going to play into that, and based on that, they will choose whether it's immersion cooling they're looking at, cold plates they're looking at, or two-phase immersion. And some of the learnings we have had, for example, I mean, it's always a mixed bag. Where we deployed 250 megawatts in single-phase immersion, it was great for performance, reliability, longevity of the hardware, but then it's not fun to deal with that messy oil. And anytime you service the servers, you're dripping the oil, and then it's a hazard for people walking around.
We just talked about that.
Yeah, so everything has a little bit of their problems, and we are all trying to just hold on to the good parts of it while trying to fix those problems, and hopefully we'll get to a solution which is, meets most of the needs.
So we know that workloads are driving the need for liquid cooling. Are the current facilities' power and cooling already maxed out for what we need? Is there a future planning effort? You said one application's not going to fit everybody's need. So let's talk a little bit about that.
That's a two-part question. So I think one of the easier ways to look at it is, or the way I start by looking at it is there's a lot of data center facilities, especially in this area, that were designed even within the last 5 years that are, you could say, tapped out. We are in the era of the megawatt plus rack. It's coming. How real that actually is, day by day, it looks more real. And a 10 megawatt data center, that's cool. You're going to have 10 racks or 8 racks in that, and that's going to be it. So there's that piece of it that's coming, and it's going to be liquid cooled, and the applications are going to drive that. The other side of it is technology is not a one-size-fits-all, just like the application. The geographic location, what you're trying to accomplish, and I think probably one of the biggest overarching statements I'd make is that air is not going away. We're in a hybrid data center era for a long time. The liquid footprint today is small. It will grow bigger. How much and how fast depends on how a company uses that, but direct-to-chip is not the solution. Immersion is not the solution. Rear door is not the solution. It's a combination of all of those for what works to support the application and the business. Geographic location, business outcomes, and things like that. It will be a mix of technology. So from a planning perspective, can the power be increased? A lot of markets are starting to show that there's power constraints. Okay, so now we go distributed. Now we go decentralized. Now we go edge. We find where that power is available. We get what we can, and we deploy there. We need a mix of technologies to manage this in this dispersed environment that still make it easy. Give better reliability and things like that. Then the other side of it is I think we have to do as engineers these power demand calculations for setup, and I think the thermal calculations have to change. The thermal demand load calculations, going from air calculation to the liquid, your delta T's change, your physical plant performance changes, that has to be accounted for. So a 10, 15-year-old data center, the physical plant performance will be drastically different as more of that footprint becomes liquid cooling, and that's got to be sized for efficiency. And that gets back to the constrained power markets. You want more power from the utility, and they say no. What makes the money? Chips. Chips make the money. So we want to put every possible watt out of a 100 megawatt pipe, 10 megawatt pipe to chips that make money and minimize it everywhere else. So you've got to be designed for efficiency the whole way through. And I think the last rounding that out is it's not just going and buying a CDU or buying a rear door. There's a hell of a lot more to it. There's process changes now that liquid is in your environment. There's literally planning changes. Can your floor load or your slab or your container or whatever handle the weight load? Liquid systems are heavy. A gallon of water weighs 8.43 pounds. That's a lot of weight. If you're putting piping overhead, it's not putting it into the existing structure. You're literally going to have thousands of pounds of additional weight sitting up top there. As you start getting more dense in power, you're adding busway, which is considerable weight. All of these things add, we have to plan for that, and we've got to know what's in it. And the last piece is now we're introducing liquid. How do you service it? You brought up a great point. Immersion is generally, I love it thermally, and that's where it stops because then I have to touch it. You generate a waste stream that can't be thrown in the garbage. If you're using PG25, you can't dump it down a drain. You've got material handling, you've got working around liquid systems, whereas before we didn't have that. So there's process changes stem to stern that need to be factored into. I'm not just buying a CDU or rear door and deploying it and my problem is solved. There is no silver bullet technology or solution. It's a complete overhaul of how an air data center is operated to move to liquid.
Yeah, no, I think, Matt, you covered it all and summarized it very well. The original question about basically how these racks and wattage is evolving, there is no doubt about that. That's growing tremendously. It's not a question of if, it's a question of when. In fact, we pretty much know even when, based on NVIDIA CEO's forecast of Blackwells and Rubins Ultra after that. We're going to go with Blackwells, we are looking at 120 kilowatts per rack, and with Rubins Ultra, we are looking at 600 kilowatts per rack. Imagine, a couple of years ago, I was looking at racks which are no more than 20 kilowatts. So for all the people who raise their hands that they are involved in some aspect of the liquid cooling industry here, it's great news. This is a problem which exists today with no solution. NVIDIA is trying to hone in and refine their direct-to-chip systems. They are also looking at immersion cooling, but there is no clear market leader, as we all know, in this space. So 600 kilowatts of rack is going to require some crazy thermal management. And that opens up opportunities for all of us to skin that cat in whichever way we think is best possible. Not only that, that AI now has to be deployed on the edge. There is military which wants to deploy this inference AI on forward basis where they don't have internet connectivity, and a whole bunch of other customer segments. And they need, as Matt mentioned, they need that actually all that AI and 600 kilowatts to be based on a high mass moving vehicle which can tolerate the acceleration and oscillations and tilt, and there is no HVAC, there is nothing. And so how do you do that? That poses a lot of very cool technological challenges, which I'm sure people will solve, but we're nowhere close to solving them.
So hold on to that for a second. So let's pivot to planning, right? You had said, Matt, it's all about modularity, scalability, and zoning. So let's talk about how are we planning today for what we need to do. So you brought up some good things. AI is driving it, all these different, healthcare, pharmaceutical, pharma's all starting to use AI. So let's talk about planning your infrastructure around the liquid cooling.
Well, it's certainly different. When you see that hockey stick curve up in terms of power and then thermal and cooling needs for that, the whole way we've done it in the past doesn't work. It's just making it bigger is just like saying hope is a strategy. It's just not going to end greatly for you. We have to take a different look. It may be painful, especially you drive down next to Dulles Airport. There's tons of data centers under construction, and whether they're going to be AI factories or not doesn't matter. But there will be a need for those types of facilities. But to truly optimize this, at the rack level, you're talking a 600 kW rack. But let's also look at some of these other applications in robotics. Cool, robot. It's not a 35, 40 watt processor PLC in there anymore. It's a 600, 800, and you're trying to get that in the smallest spot. That's going to be a liquid cooled chip. It's just going to be on a thing that's moving. And how do you plan for that? Okay, that's one thing. But as you start scaling those micro technologies that are going to be developed for that, how does that scale to help us in the data center space? So the whole planning paradigm is going to change. The concerns that you need to plan are going to change. The layout, like networking and latency. Backhaul latency is actually going to become more and more of a thing. As you distribute, you're going to distribute to offload that backhaul network. If it's local with that distribution, you're probably going to lay your own infrastructure for that. So that, again, most likely won't be liquid-cooled infrastructure supporting that, but we'll have that air element. So you've got to have these hybrid facilities, and that's only going to continue. And how do you get the most reliable technology for that? Weight, power provisioning, and again, the power is only on the uptick. It started a couple months ago as, yeah, there's a megawatt rack coming, and then it went to 1.1, and then 1.3, and now it's at 1.4. And that's not the schedule moving to the right. That's the same point on the right that just keeps going up in power. So whether that becomes a reality or not, but the fact that it's on the radar and it's in under 5 years, 600 kilowatts is the easy one. And solve for 1.4. That's a whole different way of doing things. So again, planning process, services have to be done differently, and how you go to do that is understanding what's that air-water mix, or air-liquid mix, what's the technology that's going to work now, and I think from a long-term planning, I'd round it out saying it might be water-based liquid now, but it probably over the next 3 to 5 to 10 years is certainly not going to stay water-based for these upper-end applications. So how do we make the investment today and be able to leverage that infrastructure long enough while allowing us to make the change from either 3-stage liquid or to 2-phase liquid or, bespoke refrigerants? And you're just going to have to, there's no one technology, and you're just going to have to work through it. You said it best. We're going to skin this cat together. There isn't there's a dominant technology today with liquid cooling, but it's not the only solution that works, and different things work for different people.
Yeah, and I can share some insight from our own business, how we operate, to maybe answer part of that question. When we select a site or we even start planning a site, liquid cooling is an essential planning step on day one. We decide where the site is going to be, where the power is going to come from, is it grid connected, behind the meter, what hardware will go there, how to monetize it, and what is the cooling technology. That's a key decision day one. And the fact that we have this myriad optionality of liquid cooling options available today has actually alleviated to a large extent the options we have available for sites. We all know in data center space we are running out of power. ERCOT, all the grid operators, they're no longer giving interconnects without you being in the line for 5 years, 7 years. But there is a lot of power available. It's just not grid connected. If you are willing to go behind the meter, if you have an interruptible load, if you are able to operate in locations, geographical locations, which was previously not possible in Sahara, Sub-Saharan Africa, Ethiopia, UAE, which is possible through liquid cooling, then it opens up options for cheap power. And some crazy ones, actually. So a couple of years, we started talking to University of Maine. Some of you may have heard. They have an offshore floating rig project where they're generating currently, I think, 30 megawatts, but their plan is to generate enough power to power the entire northeastern seaboard, 3 gigawatts of power. But the problem with these windmills is they are 12 miles offshore from the land, and building the windmill is easy. The communication and the power cabling to the land is very, very expensive. So they're looking for data centers who can be co-located on the rig without any power. The power is coming directly from the windmill, but who have very little communication overhead and can operate in that tiny, cold, marine environment. And there is no way you can do that with air-cooled environment. It has to be a hermetically sealed, some sort of liquid-cooled setup.
That's very interesting. So hand that back to Anshu. I'm gonna let him answer this one first. So let's move to operational realities and talk about big, ugly leaks. Because when you talk about liquid cooling and all the money we spend on electronics that are going into these stacks, how do we set up processes and procedures, or what are you guys doing today, or what do you see happening today to, prevent those operational realities, right?
Absolutely. So just like with any planning and operational business, we do the pre-mortem and the post-mortem, but that's easier said than done. These things, these technologies pose so many challenges that sometimes they are just very, very difficult to see ahead of in time. I can tell you that no matter which liquid cooling technology, they all come with their own bag of problems. I briefly talked about the single-phase immersion liquid cooling technology, which obviously have the problem of dealing with the oil, with the smell of it, the viscosity and the slipperiness of it, but also does not allow for, because it's a open bath tank style deployment, it does not have individually modular and hot swappable servers. So you have to shut down the entire tank if someone has to put their hands in it. That's one problem with single phase immersion. Direct to chip cold plates is better and seems to be the de facto leader in this industry, although I agree with Matt that 3 years, 4 years down the road, for very high performing chips, they will probably not be hydro based. They may be cold plates with some vapor chambers, some two-phase immersion cooling or something else, but hydro is not going to be able to keep up with the growing TDP requirements. Currently, the challenges we see with them are that a lot of times people don't want water around their hardware. I mean, these are laser welted narrow channels, and they can leak once in a while, and you have millions of dollars of hardware which is going to get destroyed. So we try to mitigate it with clever humidity detection and water detection wicks, but they have their own downside. They're not 100% fail-proof. Then moving on to, and then they have the other problem of scalability. We work in the mining space. We have multiple different vendors like Bitmain, MicroBT, and Canon, and others. And the hydro plates or the cold plates have to be custom built for every single die, every single socket. And so we cannot achieve economies of scale because we cannot have the same form factor for every server we are getting. And that makes it very non-scalable, very expensive solution. Then we are also experimenting with two-phase immersion cooling, and that although in terms of performance and TCO is probably the best technology, but on the TRL level, technology readiness level, it's also on the lowest amongst others. Because on one hand, we are dealing about the perception around PFAS, the coolant, and the fluid interaction that happens there. On the other hand, it's a very engineering-wise, it's a very complex system. It's a pressure vessel. It's essentially like a pressure cooker. We rely on a lot of sensors and SCADA systems and automation to make sure it's safe and it operates, goes up and down based on the environmental conditions. But if anything goes wrong, then we are looking at a pressure vessel exploded, leaking, or things like that.
Yeah, and there's not much to say on the back of that, I'll put it that way. But the one thing with liquid cooling is leaking. It's not an if, it's a when. It's going to happen. From a manufacturer standpoint, there's enough experience across the various infrastructure vendors that we know how and where to position the leak points to sort of control that. Call it minimize the blast radius or the effect of a leak. And that's kind of critical to any solution design, especially when you get into a new technology. You're just trying to get a technology to work. Then you'll start dialing in on what are the next set of problems that we need to solve. But yeah, there's pros and cons to every solution. You know, rear door doesn't have the liquid on the IT and it's on the back side. It's very low risk in terms of what happens if there's a leak. You start water-based liquid, conductivity issues. I mean, you can pump an oil through there like a dielectric that doesn't conduct, but has a way lower thermal pickup than water-based. And refrigerant has a leaking issue. It's a pressure vessel, and that has to be managed with pressure. So it's a much more complex system. You're managing that boil off or that phase change by managing the system pressure. And these are all the challenges. And as we go forward and you get into more, right now NVIDIA is the leader. They're out in front. It's a set of technology. And eventually there's going to be more players in the space. So what you're doing for maybe an NVIDIA solution today isn't going to work for an AMD solution tomorrow. Different temperatures, different flow rates. Now you start getting into other challenges with not only managing it, but designing for these fail-safes and controlling that blast radius. So it will leak. It happens. I put 250 gallons into the bottom of a raised floor one time. Things break. It happens. You deal with it and you move on, you learn. So it's never happened a second time.
All right, so let's talk about business impact and some efficiencies. So what are the ROI signals that are most compelling to leadership when you say, this is what we want to do?
Chips make money. We need the chips, so we need liquid cooling. It was not always the case. It was, prior to this, it was we want to be efficient, different drivers for efficient and being that efficient, but at the end of the day, nobody's going to spend $1 if they're not making $1.50 on the back of that, and that's the honest truth. So Liquid enables a technology that they can monetize and make money on that and generate revenue. And if that's what is needed to generate that revenue, then and there's a market for that offering, then we're going to spend the money to do that. The efficiency side of it plays in. It's spun a lot or greenwashed and say, oh yeah, we're doing it because it's efficient. We're doing it because we have to. The other benefit is compared to air, it is a lot more efficient. So we get that just by doing it, but we're required to do it. And that's really what the ROI drivers are. You can get into maintaining a liquid system can be more expensive than an air system because there's more components and they're more expensive. So your PM, your ongoing service, you've got to do liquid quality monitoring. You've got to change and service your filters. These are additional steps to all the things that you used to do with air. So ROI is definitely a different calculation, but from an operational standpoint, liquid systems are more efficient, widely known.
So Anshu, I want you to answer that question as an owner-operator and also building with, you have the mining and the other. It's a different ROI situation for you.
Absolutely. So I'll share one example actually. Exactly the AI hosting part that we are foraying into now. We are using ASICs for inference AI at the edge. And when we talked to the manufacturer, they told us that yes, they are struggling to cool these chips because these are ASICs. ASICs generate a lot of heat. And if we can cool them more effectively, their theoretical simulations show that we can overclock these ASICs 20% more. Hence, you get 20% more hardware for the same capex. You have immediately lowered your capex by 20 to 25%. That's a direct impact to the ROI and bottom line. Exactly like Matt said, chips make money, and liquid cooling allows chips to make more money. And I'll extend that thought even further. I would go so far as to say that AI and cooling are two sides of the same coin. I mean, look at the AI boom. What is driving the valuation of NVIDIA GPUs? It's the demand for bigger and bigger GPU clusters which can operate in a coherent memory space to be able to tackle the models of future from 4 billion parameters to 100 billion parameters. And NVIDIA is trying to finding it difficult to create those clusters because chips are not scaling with Dennard scaling anymore, and their NVLink technology can only connect 72 GPUs. So they have no choice but to make more and more powerful GPUs. And they're not making the individual dies more powerful, they are just adding more dies. Sometimes stacking the dies, sometimes actually putting more dies in the same chip. So Blackwell says 2 dies actually, they call it 1 GPU, but essentially it's 2 GPUs. And what's that leading to is basically now they're hitting the envelope on the cooling performance. So if someone can provide them the unlimited cooling performance, then they have essentially solved the AI GPU scaling problem. They can keep making these GPUs more and more powerful to be able to handle more and more powerful models down the road.
Anything to add?
No, that's a great
Are you
answer.
sure?
I always have a comment, but I know you want to get to another point.
Yeah. So let's talk about looking into the future. Where does this all go? I want your technical opinion, and then I want your real world opinion. And then we'll go to some questions.
I mean, I've already hit on a bunch of those topics. I think we've hit on a bunch of those topics together where it's going to go. There's going to be a technology leader out there that's going to keep raising the bar for thermal, and that's what's going to force the next technology to come in. That's going to move a lot of customers away from water-based liquids or other technologies. But you also have a whole bunch of stuff today in the enterprise space that's, 5 years ago was chirping away at a 100-watt TDP chip. Today is a 300-watt TDP chip that's still air and will most likely hit 600 watts. And you're saying, hey, I'm 40% liquid footprint. Why don't I make the change because my server vendor offers that as well? And I've already got the infrastructure. I know how to work around it. And that business will make that change where those enterprise workloads will pick up. Meanwhile, NVIDIA, AMD, other ASICs will be sitting in the 2, 3, 4 kilowatt per chip range. Again, assuming that thermal performance is solved, and that's not like a complete gate. So you're going to have the SMB space. You're going to have the enterprise workloads move to that because there's performance advantages in those chips, and there's going to be a point where, hey, we've got this in, let's do it. There's also going to be a point where today I'm using crawls around my data center, and tomorrow I'm going to be using rear doors because I don't want to put more crawls in. It's actually just cheaper to use rear doors. So that water is coming closer to, or the refrigerant is coming closer to the IT rack. So there's going to be multiple solutions. There's going to be multiple tiers. And I think I'll move on to the personal opinion is 6 customers got all of the 2024 and 2025 allocation of GB200. 6. So now that they've got their allocation and their next focus is on GB300, cool. Now everybody else can start getting GB200s, just like everybody now is getting H200s and H100s. So there's going to be multiple of these that are coming out. H100 was big. H200 was 40 kW a rack. GB200 was 120 kW per rack. That's a big jump for essentially the next iterative technology. It's going to keep going. So now you're getting into the bigger customers, finance, insurance are going to pick up GB200 as that comes available, and then you're going to start filtering down. And this only happens because new AI use cases come up every day. Again, it's not just chat bots, it's a whole bunch of other applications and use cases and things like that that are going to drive very specific needs. Will they be dropping 72 GPU clusters? No. They'll have 1 or 2 systems. They'll have 8. They'll have 16. That's what they need. But those chips will require liquid cooling. So big or small, they're going to go down this path one way or the other. So there will be continual technological innovation in the liquid cooling front, and I actually think what I like about it, as my FAE says, we're in the golden age. It truly is, because we are literally going to use AI to solve all of the problems caused by AI. And we start seeing it today, and that's just going to continue. And where that ends up with is pace of innovation. The pace of innovation in the last 10 to 15 years in liquid cooling was glacially slow. There's a CDU that was in the market for 15 years, and it still worked at the end of its life. And 3 years later, it was about 25% of the capacity it needed to be. So that's how fast we ticked up. There was no standardization in the market 15 years ago, and now we're largely standardized on a few common interfaces. That's a huge step forward. That makes this stuff digestible. That makes this easier to install than being I've got to do all the design work and bespoke, part solutions and everything, because none of this existed. So we're getting to standardization. We're getting rapid technological advancement. We're going to get new materials that are going to come out of this. And out of that process there, we're going to get new standards, new guidelines, new best practices. I just love how fast it's moving. It's kind of scary, but that's kind of the interesting part.
Do you remember the question?
Mm-hmm.
Not you.
I hope so. I'll try. Then you can correct me. No, I completely agree that right now we are in the middle. It seems like a bit chaotic because we are being driven by this opportunity, but it's day one. But I think over time it will lead to standardization. People will figure out what their core area of expertise is, what they're best at, and we will learn to work with each other, and we will come up with some cool integrated technologies, cooling technologies. Will it be one? I don't think so, but I think it will be a few. It won't be the constant experimentation learning that we are going through today. Obviously, we have to at some point stop learning and just start executing. And I think in large part it will be driven by 3 main customer segments. One will be your edge AI, which is, again, very early innings for that, but it's going to grow. There is clear proof for that. Smart cities, telcos, all of them are expanding. Vehicle-to-vehicle mesh networks, residential and commercial siloed data centers, all those are happening today, and they will keep growing. So that will be maybe one type of liquid cooling that you'll need. Then you have the hyperscalers, which don't traditionally buy from anyone. They like to do their own, make their own solutions. They will build their own customized buildings and servers, and they will build commoditized solutions from large vendors. Probably that will be some shape of or form of direct-to-chip cooling, cold plates, because that's where their head has been. And then there will be the traditional enterprise server segment, which is all your digital realty, co-location data centers, financial institutions, Walmarts, etc. And that is still nebulous because, again, we have to reach a standardization of the servers first, and then we figure out what liquid cooling technology works best for that. Some people may continue to just hobble along with air-cooled for as long as possible, and others may be more innovative and choose to go to immersion or direct-to-chip. But that's TBD. But I am for sure that liquid cooling is going to find its way to the hyperscalers because it means dollars, TCO improvements to them, and also to edge because the environmental factors, their space constraints, they just need that liquid cooling technology today.
Thank you. All right, do we have any questions? I'm going to come out with the microphone.
Thank you, gentlemen. Remarkably helpful information you provided today. I'm Steve Aubuchon. I lead the business development group at W.L. Gore & Associates, our materials company. And my question for you is maybe to kind of summarize this wealth of information that you provided today. I'm going to ask you the cliche question, the magic wand question. If you could wave your magic wand and instantaneously improve some aspect of the performance or potentially the value of liquid cooling, what would that be?
That's a great question, by the way. Thanks, Steve, for that question. Made me think. Like I said, we have different liquid cooling technologies that we are experimenting. So I'm going to talk about the one that I find most promising, and that's probably what Matt said, an evolution of direct-to-chip into two-phase. So maybe a two-phase direct-to-chip liquid cooling technology. And the biggest, if I could magically wave my wand, one thing I would like for ODMs to do is basically standardize not their 100% of their hardware architecture, but some parts of it, so we can commoditize those cold plates and achieve economies of scale. The CDU part we have, we can, it's very generic. It can be, is different from the traditional CDUs, but it's irrelevant. It does not impacted by the hardware, but the cold plates, and these are copper cold plates, so they are very expensive. And the manifolds, those can be standardized if we have server standardization, and that's what I would hope for.
Yeah, I mean, we're approaching this from two different angles. On my side as an infrastructure developer and vendor, yeah, I think where the industry's at today is we are getting to very similar CDU footprints from the various vendors that are out there. The sizes are sort of, or jumping blocks are sort of known. Where it gets to is if I had to wave my magic wand and be this easy, yes, two-phase closed loop solutions like two-phase cold plate, that's going to be where we're going to spend a lot of time in the future. Today where we're at, it's just, sort of getting around the specsmanship. I wish we would all speak the same language. TDP was a really nice factor because it gave you the heat load that you had to accommodate on that chip. But now when you've got different flow rates and different capacities of CDUs at different approach, like there's a number of things that can affect that, and not all 2 megawatt CDUs are created equal. We'll put it that way. Not all 2 megawatt CDUs are actually 2 megawatt CDUs. So from the infrastructure side of it, what makes life easy, and I think is coming to an understanding of when we call a CDU and it's X number of kilowatts or megawatts, what's that formula? I mean, there's work going on within ASHRAE to develop that standard, but that's still a while off. But that would just make life easy. And if the IT vendors or the silicon vendors would go ahead and, well, a TDP is one thing, but give me a TDP and a flow rate. That way I can make sure that the CDU aligns with that. I think that's a pretty simple thing that makes end-to-end system design from a customer perspective at any level really easy to digest. You know what your IT is going to require. You know what your CDU is going to provide. That's pretty easy to be able to marry those two numbers up. Right now, you pretty much need a PhD or 20 years of experience to figure this stuff out, and it shouldn't be that hard.
Anybody else have a question?
I had a question regarding and we kind of hit on it before, which is the the hesitancy to go to liquid cooling. Are you still seeing that in terms of we know the chips demand it, but still, I don't want to go to liquid cooling. How much of that are you still seeing, and do you ever really ever expect that to go away?
I would say before it was resistance and now it's fear, and that's just an unknown. You're doing something in a data center and you're going to be responsible for doing something in a data center that you don't necessarily have background or expertise to do. And again, water-based fluids around electronics typically don't play nicely. That can be a very, very expensive mistake. So it is fear of not screwing up or fear of the technology. It's just a fear of the unknown. Before there was a resistance, we're not going to do it because I don't know it, and we don't need to. Now that I need to do it, I really don't want to because I don't know enough about it. So it's not that it's a way to mitigate or get around it, but using a dielectric immersion sort of eases into it that way. Here you have a liquid cooling or a fluid that isn't going to break your IT, and then you can start working around it. And water-based and cold plates are very different, but it could be a way to get there, but it can sort of settle that fear. But probably the easiest way I think of addressing that's not promoting events, but coming to events and listening to things from people that have experience, not only on the planning side and the development, but the implementation side, to really answer those questions that are causing that underlying fear.
Yeah, the biggest challenge or hesitation I have seen is actually from the data center EPC companies, construction companies, because they just can't wrap their head oftentimes around the innovation and just how radically different it is from air cooling. They've been building these air-cooled data centers for the last 20 plus years, and they don't want to make major changes. They want to take only baby steps. And I think probably that's the reason why direct-to-chip is working better than other revolutionary liquid cooling technologies. We'll see whether they will, whether the necessity will force them to try new technologies. For some people, some of them are already doing that. At what rate that pace of innovation will pick up is to be seen.
Okay, so unfortunately, we are out of time. Got to get the big hook. But Anshu and Matt, you'll be out in front and can answer some more questions. Thank you, gentlemen, so much for a very interesting talk. I think we could talk for another hour, but thanks, everyone, for coming.